Okay, so I think we can get started. So based on the syllabus, today's topic is about network transformation. So basically, the reason why we want to talk about this topic today is that in network-related problems, there are many variations. And so for example, if you know, has Dr. Costello covered network flow problem in her lecture? Yeah, so like in the network flow problem, there might be some variations, such as say, there's not just an upper bound for the flow on each arc, but there can also be some lower bound for the flow on each arc. So in this case, if you know how to do network transformation, then you can transform this problem to something that you have learned in class, and you solve for the optimal solution by some algorithm that is also introduced in class. And then you can transform the optimal solution on this transformed network to the optimal solution in the original network. So this is the reason why we talk about network transformation today. So one thing that is very important is that for today's methods that I have introduced for network transformation, you should be aware of how to transform the optimal solution in the transform network to the optimal solution in the original problem. This is a very important thing. Okay, so basically our discussion is based on the mean cost flow problem. I mean, we start from this, and actually the minimum cost of flow problem, it can also be used to express other problems. So let me write it down first. So remember that in a mean cost flow problem, we want to minimize such that So let me interpret this. So this minimum cost of flow format is widely used in this course. So you need to determine Xij. Xij means the flow on each arc, and it should be in a range which is bounded by the lower bound and upper bound for the flow on this arc. And on each arc, we also have a cost Cij. It means that for each unit of flow on this arc, what is the cost that it has generated? And for this condition, how do we interpret this? So we see that first we want to make a summation of Xij such that Ij is in A, and we minus Xji such that Ji for all the Ji in A. So this color. So this means the outflow of I. This means the outflow of I. And this means the inflow of I. And this should be equal to Bi. So Bi means a balance of I. And please note that in the minimum cost flow model, this Bi not necessarily equals to 0. That's to say, the inflow and outflow of I are not necessarily equal. But for this format, can anybody tell me how can we express the max flow problem using this minimum cost flow problem, using this minimum cost flow model? Thomas, can you tell us? In what case does this express the max flow problem?
Where if all transshipment nodes, for all the transshipment nodes, bi is equal to 0, and for the source, it's f, and for the sink, it's n.
Yes. So what you want to maximize is just the flow out of the sink, right? So for let me say it again. So for all the transshipment nodes, the inflow equals to the outflow. This makes sense. And for the and we know that there's a source called S and there's a sink called T. So the outflow of S is equal to the inflow of T. And what we want to maximize is the outflow of S, which is equivalent to maximizing the inflow of T. So this is for the max flow problem. So what I can comment for this model is that this is just a generic representation. This is a generic representation. And actually, it can also be, this format, this model can be used to express the shortest path problem. Shortest path problem. And say max flow problem. And also assignment problem. So after this class, you may think about how to use this to express shortest path problem and assignment problem. Okay, so next, let us introduce the techniques. So the first technique technique 1 is from the undirected arc to directed arc. So what does this mean? In some problems, there might exist some undirected arcs, let's say from I. This is a node I, this is a node J, and however, this is an undirected arc between I and J. And also for the flow from I to J or from J to I, it should be below the Uij. And for this kind of scenario, we can transform into I and J. This is very straightforward, right? To transform a undirected arc to a directed, that's to say, you add a directed arc from I to J and also a directed arc from J to I. And what else? So when you do this transformation, you need to note these things. First, Ij and Ji. They both have unit cost Cij. So that's to say, if there's one unit of flow from I to J, the unit cost is Cij, and if there's one unit flow from J to I, it's also Cij. This is what you need to be careful. And the Uij equals to Uji. It's equal to U. So here I need to clarify. Say suppose for this undirected arc is capacity is U. Okay. But here, if you want to do this transformation, there are two things that you should be very careful. The first thing is that Lij must be equal to 0. This is given in a textbook. So the first thing that you need to be very careful when you want to do this transformation is that Lij must be equal to 0. Or in other words, this transformation is no longer valid if Lij is greater than 0. This is the first thing that you need to be very careful. And the second thing is Cij should be non-negative. So I give you 1 minute to think about why we need to satisfy these two. Or in other words, what if say Lij is greater than 0? Why this transformation is wrong? And what if Cij is less than 0? Why the transformation is wrong? So I'll give you 1 minute to think about it. Anybody has an idea?
Second.
Please.
Cij.
So please speak.
If the Cij is negative,
Okay.
it would create a negative cost cycle, I suppose. It would be
Negative cost cycle. So you mean from I to j and j to I, this is a negative cost cycle, right?
Yeah.
Yeah, and in this way, because we have uij equals to uji equals to u, then for the optimal solution in the transformed problem, you need to maximize the flow from I to j and also maximize the flow from j to I, right? But this is different from the optimal solution in the original problem. Is that correct? Yeah. So this is the explanation for the second point. And for the first point is that if Lij equals to 0, so what does this mean? If Lij is greater than 0, if Lij is greater than 0, what does it mean? This means that you either Xij minus Xji. This is larger than or equal to Lij. Because if you transform the solution on this problem into this problem, if Xij is greater than Xji, then it is equivalent to there's only flow from I to j. And if Xji is greater than Xij, it means that there's only flow from j to I, right? So if you in this problem, you transform there's two units of flow from I to j and 1 unit of flow from j to I. Then it is equivalent to say there's 1 unit of flow from I to j in the original problem. So if Lij is greater than 0, then either Xij minus Xji is greater than or equal to Lij, or Xji minus Xij is larger than or equal to Lij. Is that clear? Either case should happen, because let me explain again. So the flow on Ij in the original problem is just the absolute value of Xij minus Xji in the transformed problem. So either case should happen. However, there's no way to integrate this condition into the original problem's condition. So I think this is the reason why we should set this restriction. So in your textbook, if you read it, the authors just say, okay, so Lij should be equal to 0 and Cij should be non-negative, but they didn't tell why. So this is my thinking. Okay, so this is the thing that you need to memorize. So how to transform a solution in this transform network into a solution in the original network. Okay. So the technique technique 2 is called remove non-zero lower bound. So what does this mean? Let's say we have a node I, node J. This node I should have balance BI, and node J should have balance BJ. And say we have an arc from I to J. And this arc, it has unit cost Cij, and the maximum capacity Uij. And the flow is Xij. And of course, Xij should be less than or equal to Uij and greater than or equal to Lij. And now, if Lij is strictly greater than 0, then in this technique, what we do is that we send Lij units from I to J. Then what will happen? So think about this problem. That's to say, from the original problem, now we force the node I to send Lij units to J. Then what happens to these two nodes? Now, sorry, I need to change the color. So now, the balance of I and the balance of the J, how will they change? I have already forced node I to send Lij units to J. Then what will happen to the balance of I? So, and also you should note that the balance of I equals to the outflow of I minus the inflow of I. This is our formula. So I has already sent Lij units to J. Then how will the balance of I change? So now the balance of I it should be Bi minus Lij. Because the outflow of I, for the outflow of I have already guaranteed there should be Lij units because it is sent from I to J. So now the balance of I becomes Bi minus Lij. And accordingly, the balance of J, now it becomes Bj plus Lij. And the flow variable, is say Xij prime. This Xij prime should just be Xij minus Lij. So what does this mean? Suppose the Lij is 1, and say you have Xij, you have 4 units of flow from I to J, and the lower bound is 1. So now the Xij prime means the excess flow from I to J. So when I say the excess flow, it is with respect to the lower bound. So if say Xij is 4 and the lower bound is 1, then Xij prime, the excess flow is just 3. And so that's to say, for a network, if for some arc we have the lower bound not equal to 0, it is greater than 0. That's to say, for every arc ij, note that this is for every arc ij. For every arc ij, we do this transformation. We make the balance of I to be Bi minus Lij, the balance of J to be Bj plus Lij. And then, and of course, now the Uij prime. And now the upper bound becomes Uij minus Lij. So that's to say, this is the upper bound for the excess flow from I to J. And then we solve this transform the network. And we know that now the transform the network, for the flow on every arc, the lower bound becomes 0, right? what do we get for the transform the problem? So in the transform, so now if we solve for the optimal solution in the transform the problem, the flow on every arc means the excess flow. The flow on every arc is the excess flow xij prime. And if we want to transform back to the optimal solution in the original problem, we just add Lij back to xij prime. And in this way, we obtain xij. This is the optimal solution for the original problem. Is that clear? If you have questions, please ask. This is very important. So based on my memory of this course, last year, we encountered some problems saying that, so what if the network, in the network now, we add some restrictions. Let's say the flow should be, the lower bound of the flow is strictly greater than 0. How should you transform this problem into another problem that is introduced in class? And in this way, you can use some existing algorithms to solve it. So make sure that you understand this, you understand why. And if you have any question, just raise your hand. Okay, so if no questions, then I will continue. So the technique 3. This is called arc reversal. So I have to admit that this technique, I have not encountered any problem which need to use arc reversal technique, but I just introduce it because this is introduced in the textbook. So arc reversal, it is used in the case such that Cij is less than 0. So for some problems, in a problem, you will be told that, say, Cij is less than 0 for some arc I to j. What does this mean? This means that for the flow from I to j, the more flow is on I to j, the less cost you will encounter. So this is different from the original setting, such that we assume Cij is greater than or equal to 0. So how to do this transformation? Say this is I and j, balance bi, balance bj, equals to Cij and upper bound is uij. Okay, so this transformed to, this is I, this is j. Then, based on the name, arc reversal, you know that originally there's an arc from I to j. Then, if you reverse it, is j to I. And now, because it is j to I, then the unit cost from j to I is just a minus Cij. This is intuitive, right? Minus Cij. And also, and the upper bound for the flow from j to I is still uij. And a very natural question is, what does this mean? Why do we need to do this? So so for this transformation, this is equivalent to, say, I think I need to write the explanation here. Interpretation. The interpretation of such transformation is that you send uij units from I to j. And then bi becomes bi minus uij. This is similar to what we introduced before, right? Because I have already forced uij units to be sent from I to j. Then the balance of I becomes bi minus uij. And the balance of j becomes bj plus uij. So now, for this problem, the unit cost becomes negative Cij and the capacity is still Uij. Then if we solve for, say, we have flow xji in the transform network, what does this mean? This means that, so interpretation, based on the interpretation, we have already set Uij units from I to j. Then this xji means that how much we need to take away from Uij. This is the meaning. So let me explain again. When you do this transformation, it is equivalent to, first you have already sent Uij units from I to j. But this might not be the optimal solution to the whole problem. And then for this transformed problem, you solve for the optimal solution and say in the optimal solution, you obtain the flow xji from j to I. This means that how much, xji means that how much you need to take away from these Uij units that you have already set to j. Is that clear? To make an analysis, this is just like in the optimal solution, I need to pay you, say, $7. So first I pay you $10, and next you need to give me back $3. This $3 is just xji. This is an intuitive explanation. And for this technique, we will also introduce later in the residual network technique, which will be introduced later. So, okay, this is for technique 3. Okay, so technique 4. Technique 4 is called removing arc capacity. Guess what? I've also not encountered this kind of problem before. So actually, there are many contents that are introduced that is introduced in the textbook, but not all of them are used in problems. So for this technique, I think you just need to memorize how to do this. But I have not encountered any problem about it before. So still, I to j, the bi and bj, cij, uij, right? And the flow is xij. Then for this transformation, it is transformed to I, and you add some intermediate node k, and then j. Then the transformation is just like plus uij. And now for the arc from I to k, the unit cost is still Cij, but now the upper bound becomes positive infinity. And for the arc from j to k, it has unit cost 0 and upper bound positive infinity. And for the k, it's negative Uij, means that for all the flows that come to k, because we know that k only accepts the flow from I to k and the flow from j to k. So that's to say the total flow should be minus Uij, and it's xij, sij. So I think you must be very confused. What the hell am I doing here, right? So if I write it this way, equivalent. This is equivalent to. So remember that when we introduced the simplex algorithm in linear programming, we have something like this, but we have a technique called adding slack variable. We can make it to be xij plus sij. And this is just a uij. So sij here means the slack variable. So if you want me to interpret this, what I can say is that, so now the xij has no upper bound. It can be any positive value. It can be any value. And xij means that how much I gives to j. And sij means that how much j returns to I. So just using the same analogy, it is like the payment that I should give to j should be below, say, $10. But now I gives $20 to j. Then what should j do? J should return $10 to I, right? This is my interpretation, but never mind. As I said, I have never encountered this technique before. But the next technique is very important. So the next technique is called node splitting. So first, I think I want to introduce to you a more useful node splitting technique, because actually for the node splitting technique that is introduced in the book, it is still very confusing. By the way, I have to say, there's one agreement between the other TA and I. The agreement is that we both feel that the book is too old and it is not that, it is not quite good, because for some techniques that is introduced in the book, it is just quite confusing, right? So we have to admit this. So first, in terms of node splitting, actually I encountered this before. So suppose now, let's think about this. In the network flow problem, in the max flow problem, say in max flow problem. So in max flow problem, we know that for every transshipment node, the balance equals to 0, right? In equals to out. So in max flow problem, for any I, which is not equal to S, source or sink, the balance of I is just equal to 0. This is totally in the class. Then suppose I add one more constraint. The constraint is that the flow that come to I should be below some threshold. That's to say, we know that bi equals to 0. That's for any j such that ji in the arc, the xji. We know that this is equal to all the j's, ij in the arc, xij. This explains bi equals to 0. However, in some problems, there might be one more constraint. That's to say, sigma say j in a xji. If this should be no more than some value ui, then what should we do? So remember that, what does a max flow problem mean in real life? It means that, so the source is like some manufacturer, and the sink is like, say, some retailer, and the transshipment node means that you may have some warehouse in the between the manufacturer and the retailer, right? And you want to maximize the flow. That's to say, you want to maximize the efficiency for transportation between the manufacturer and the retailer. However, because we know that the transshipment nodes, they mean warehouses. So for every warehouse, they cannot, they have a limitation every day. Let's say they can only process, say, 100 tons of loads every day. If you give them, say, 1,000 tons, they cannot do it. So that's the reason why, in some problems, you may encounter such constraint like the flow that flows through the node I should be below some threshold. Then how can we deal with this problem? How can we transform this problem into the original max flow problem? So remember that in the original max flow problem, there's no such restriction. How can we do this? Based on this name, node splitting. Sean, do you have an idea? Based on this name, node splitting. What does a splitting mean? One node, then it becomes two nodes. How can we integrate this restriction into the original problem? Thomas, you have an idea? Okay. So I introduced this here. So let's say originally this is node I, and we have some flow that goes into I and some flow that goes out of I. And there should be a balance. The balance equals to 0. And now, because I want all the flow that flows through I be less than or equal to some threshold ui, then when I do the node splitting, I split it to be, say, I1 and I2. And there's an arc between I1 and I2. For all the flow that gets into I, it flows into I1. And for all the flow that flows out of I, it flows out of I2. But this arc is very important. This arc has an upper bound ui. Think about this. Now I have splitted the node I into I1 and I2. And the arc that connects I1 and I2, it has upper bound ui. So in this way, we don't need this restriction anymore, because this arc, I1, I2, it has upper bound ui. If you just use the max flow algorithm to solve for the optimal solution, this arc guarantees that all the flow that flows into I must be no more than ui, right? Otherwise, this arc is not, the restriction on this arc is not satisfied anymore. So that's why we need to do node splitting. This is a very useful technique in some problems. Okay. So we still have 10 minutes left. I want to talk about the last technique. The last technique is called residual network. I think actually the last technique is the most useful, because have you learned the max flow algorithm in the class? That's to say how to solve for the max flow. No? Okay. So the last technique. This is called residual network. So if any one of you has once played with deep learning, you know something called residual neural network, which is widely used in computer vision. But now I need to clarify that this residual network is different from the residual neural network in deep learning. So residual network, what does it mean? Suppose you are. In a max flow problem, let's say we have a node I and another node J. Sorry, this is not very clear. So suppose we have an arc from I to J and xij. So suppose xij is less than or equal to some uij greater than or equal to 0. Now, in the max flow problem, so when you learn the algorithm of max flow problem, you will find that the max flow problem, actually what it is doing is that it iteratively increases the flow in this network. So now suppose xij is less than uij, That's to say, in the current flow, the Xij is less than Uij. Then, as I said, in the max flow algorithm, what it actually does is that it iteratively increases the flow, just to try to reach the limit. This is what the max flow algorithm do. And now, if we want to, in the process of the max flow algorithm, we want to increase the flow in the network. Then how do we deal with this case such that Xij is less than Uij? This means that for the arc ij, you can still add some flow on it. Or you can also decrease the flow on it because Xij, say it is greater than 0. So that's to say for an arc ij, you can do, if you want to increase the total flow in this network, you can do, for the arc ij, you can either increase the flow on arc ij, or you can decrease the flow on arc ij, or you do nothing to it. Actually, there are 3 possibilities. So what we do is that we construct some residual network. So in a residual network, I'm sorry, we don't have other colors for the marker. So what we do is like this. So originally, we know that there's an arc between from I to j, and the capacity is Uij. So now in the residual network, the arc from I to j, it has capacity Uij minus Xij. This explains how much more flow you can add to the arc ij. It is Uij minus Xij. Let's say you can work for 10 hours per day. Now you work for 8 hours per day. Then what's more to go? 2 hours. This is Uij minus Xij. And now I have added an additional arc from j to I shown in the dashed line. So this additional arc from j to I, it has capacity. It has capacity Xij. So what does this mean? This means that this means that how much flow you can reduce from the arc ij. Now you have already, in the current feasible solution, you have already had Xij units of flow from I to j. And if you want to search for a better solution, it is possible that you reduce some flow from I to j, but increase flow elsewhere. This is possible. So we add an arc from j to I and has capacity Xij, means that you can at most reduce Xij units of flow from I to j. And this is equivalent to, say, you send Xij units of flow from j to I. Does that make sense? Okay. So I think that's all for today's talk. So if you have any question, just ask. If you don't have any question, I think we can just end here.